Hi, everyone. Welcome to this session on data efficiency through transfer learning. My name is Eddie Du. I'm an applied research scientist at Georgian Partners. My background is mostly in computer science, so I have a master's in computer science from the University of Toronto and a bachelor's of mathematics from University of Waterloo. So in a previous life, I was a software engineer, and I'm happy now that I'm doing applied research work at Georgian Partners. So I want to tell you a little bit more about Georgian Partners. We're actually an investment firm up in Toronto. And we usually invest in technology, software as a service companies in their Series B or later, so growth stage equity. And if you're a company making somewhere between $500,000 per month or $6 million annual recurring revenue, that's right in our mandate. And we're a thesis-driven investment company, which means that we really like companies who's working in the areas of applied AI, conversational AI, security, privacy, and trust. You might be wondering why an investment firm is interested in doing transfer learning. Actually, one of the biggest value adds that we provide to our companies is helping them solve really tough problems and adopting new technology trends and new research through this in-house applied research lab that we call the Impact Team. So the Impact Team is made up of a lot of PhDs and master students or master grads from various areas of computer science, as well as a lot of industry professionals who has kind of been through the trenches. So the work that we're going to do today, so the talk today is about some of the work that we have done with our portfolio companies, collaborating with them to solve some of their tough problems. I wanted to point out something about our portfolio. So as you can see, if you recognize some of the logos here, you'll realize that a lot of the companies on this list is actually a B2B company. In fact, the majority of our portfolio are B2B companies. And there's this very specific problem that we see consistently with B2B companies. And this is the problem. So as a B2B company, my customer is another business. And usually, people would like to store a customer's data separated from other customers' data. So we see this siloed data scenario happen a lot in B2B scenarios. So when it comes time to train a predictive model on your data, a lot of people, well, the really naive way to do it is simply to train a model per customer. So this leaves a lot of opportunity kind of on the table because you can really get a lot more out of your data if you were able to actually use all of your data across all your customers. And this becomes more of a problem when you have a customer, like customer 4 here, without a lot of data. So that means probably a cold start customer, a new customer that just signed up. And if you're a company that's growing really fast, you have new customers sign up all the time, and these customers usually don't have a lot of data, but they want to see some kind of value out of your model to justify the efforts to give you more data. So the problem is really exaggerated when it's a cold start customer. So the talk today is about a couple of techniques that we came up with in solving the real life problem of aggregating data across multiple customers. How do we do that effectively, and how do we do that in the face of some privacy constraints? So here's the agenda. We're going to walk through 2 case studies of how we worked with our companies to solve this problem. The first one is from a company named Quality. And the technique here is called instance-based transfer learning. And this effectively is saying, well, can we just simply aggregate the data together in some intelligent way? The next case study is from a company named Bluecore. And the technique is called model ensemble transfer learning with differential privacy. And excuse me. And we'll require this technique when there is some privacy concerns with sharing data between different customers. And I'll explain that concern in more detail when we get there. So I want you to keep in mind that there are 3 key takeaways that I want you to have from this talk. The first is why simple aggregation of data doesn't necessarily always work. And how can we do better? The second is to give you an intuitive understanding of differential privacy, which is the foundation of how we solved our use case with Bluecore. And number three, and perhaps the most important, is I want you to walk away with a high-level understanding of these methods, enough that you can judge whether they will apply to your business problems next week when you get back to work. All right, let's get started. So technique number one, instance-based transfer learning. I want to start this by introducing the company that we collaborated with for this project. And the company is named Cority. Cority is a EHSQ software provider, and what they effectively do, their product is effectively a workflow tool for tracking events that happen in the workplace. And it's mostly used by big oil and gas companies. So as you can see, some of the logos they have at the bottom, they have like Airbus, Suncor, NASA, and so on and so forth. So they have a lot of data about what happens on a day-to-day basis with people at these organizations. And one of the things that they wanted to do was to create an injury prediction model. So trying to predict when an injury will happen. And as you can imagine, this is extremely useful for a lot of companies to save a lot of money if we can actually make this model work. The problem is that injuries happen very, very infrequently. So here we have the silo database diagram again. And in Cority's case, if we were to think of injury prediction, we have maybe like somewhere between 1 to 3% of injuries actually reported in a database. Everything else is non-injuries. So you have a massively imbalanced classification problem. So if you were to train a model on each of the data sets by itself, you would get pretty poor performance. And what we ideally want to do, so we have very few positives. What we ideally want to do is train a model that's using everyone's data in some way, and hopefully that will get us better performance. So how do we actually do that? So in order to kind of explain how we did it, I want to just show you some simple notations here. The data set that we're trying to build a model on top of, the green one on the far left, we'll call that the target domain. And everyone else's data, we'll call that the source domain. And effectively, what we're trying to do is that we're trying to transfer the knowledge from the source domain to the target domain. Makes sense, right? All right. So the first stab at this problem might be as simple as, why not just concatenate all the data together? Why not take the union of all the data that you have? And through this illustration, we'll see kind of why it doesn't always work. So here we have in the square our target data set. And the yellow lines, if we just train a simple linear classification on this data. Now we introduce the source data, which are these stars. And what you can kind of intuitively see here is that the source data is kind of overwhelming the target data. If there's a lot of source data, and usually there is a lot of source data, if you were to train a classification model on top of this, you'll see that the positive examples from our target set are now misclassified. So we got we got a decrement in performance by adding more data. And in general, we refer to this as negative transfer. So we would like to avoid negative transfer, and we want to do well on our target task on our target data set. How do we actually do that? Well, here's an idea. Why don't we put a weight on each data point in the source data set? And one way to do it, a very simple way, is that we can train a classifier to tell whether a single data point belongs to the source or target. And in doing this, we can score each source data point by how close it is to that line. And here you can see we put a weight on each data point, so the darker it is, the closer it is to the boundary. The lighter it is, the further away the point is, and so we don't really care about that point. And if we were to train a model now on the weighted data set, we get a much better result, or one that is more intelligible. So that's kind of roughly the intuition of why we want to weigh each data point, is to avoid this idea of negative transfer. In general, again, we have the source and target data sets. In general, what we want to do is to match the distribution of the source data set to the distribution of the target data set. In general, this problem is called domain adaptation. And here we've just simply taken a very simple approach to doing domain adaptation. Because in practice, it actually works pretty well, so we didn't need to explore more complicated methods. There's also some mathematical justifications on why this actually works. So here we have a pretty classic minimizing the expected loss over the target data set. And you'll see how the source data set is introduced through the mathematical notations here. So let's make some space by kind of moving the expectation all the way to the left over there. So now we have some extra space on the right. We can expand this by writing it as an integral. And then we use the oldest tricky math by multiplying this whole thing by 1. And in this one term, we've introduced alpha, which is a hyperparameter that we're going to tune. And then we introduce this probability of S, this density of the source data set. Again, if we expand this, we get a linear combination of two expectations. And the two expectations are kind of weighed by this alpha parameter. Again, this is something you can tune. The first expectation on the left is an expectation over the target data set. And this target data set is, and this expectation is the same expectation that we had before. On the right, we have an expectation over the source data set. And this is kind of the key part of here, of this method. Because every data point, the loss of every data point in the source data set is weighed by this likelihood ratio of the density of T over the density of S. And you might recognize this from something like importance sampling, and they are very much closely related. So in practice, we can actually, at least for this case, we can actually estimate this P of T over P of S, because we have too little data points in each of these domains to actually estimate the density well, because we don't have a representative sample of the population to estimate the actual densities. So what we end up doing here is just to train a logistic regression classifier and use the predictions from the classifier to kind of estimate the ratio here. And that turned out to work pretty well. So highlighted in green here is the likelihood ratio. We also call that WX, so that would be the weight for each data point. The big idea really is that if you can put some kind of weight on your data points, you'll probably do pretty well. So we can also tune this weight a little bit. So this is not entirely mathematically correct, but if we kind of include also, so in the green here, the green part is the likelihood ratio we saw on the last slide. If we can also include another weight term here that says how important is this point to the target task that we're trying to perform, we actually get a slightly better result. Again, I don't think we have a good mathematical justification for doing this just yet, or at least we didn't look into it very much, but it's definitely something that helps. So the big idea here is, again, if you can put a weight on your data points to avoid the negative transfer, you're probably going to get a good result. All right, so remember the problem that we're trying to solve originally. So we have these really imbalanced data sets. We're trying to train this model. And here we're using kind of the weighted aggregation of all the data sets together to transfer the knowledge, quote unquote, from the source data set, which is customer 2, 3, and 4, to the target data set, which is customer 1. So here are some of the results that we got from an example partner. So AT is if we train the model only on the target data set. And we see the F1 score is 0.06. If we train just on the source data set, we get slightly better recall, but we have really poor precision. This kind of gives us an idea that, well, it seems like the source covers more ground, but it is not exactly the same as our target data set, so the precision is a little bit worse. If we train on simply the concatenation or the union of the two data sets, so that's the third row, we get a slightly better F1 score, but really it's not that much better. And then finally, the last row is when we use this data point weighting idea. And we can see that we get a much better performance. So in absolute terms, these numbers are still pretty low, but how you kind of quantify the effectiveness of this approach is by looking at how much is the delta between AT, AS, and AHW here. So we have almost 100% improvement on just using the target set itself by integrating the source data. All right, so a summary of this approach. When aggregating data, put a weight on each data point. You can do it via importance sampling or via some other method that might make sense to you. In our case, we did it with importance sampling and a weight that comes from how well it helps the end target task. And that simple union of data sets may result in something called negative transfer. And you should kind of actively think about how to avoid this. All right, so that is the first part. That's the first technique. Now, let's talk about the second technique, which is the model ensemble transfer learning with differential privacy. And this might get a little bit more complicated. For this case study, we want to introduce a company named Bluecore. So Bluecore is an intelligent email marketing company. They send personalized marketing emails to each individual on behalf of e-commerce retailers. So as you can see here, they work with some pretty big retailers. And Bluecore's challenge is that they recognize this opportunity that if they were to merge data from across or use data from across their customers, they can potentially get a lot of a big boost on their on one of their predictive models. I can't remember which one exactly. But their challenge here is that they can't actually directly aggregate data across retailers. So this is a problem because, for example, if let's say Alice and Bob are part of retailer 2, they're actually the end users who purchase from retailer 2. And I want to train a model on the data for retailer 1. The problem is that retailer 2 probably wouldn't want to let me know that Alice and Bob shopped at retailer 2 because that would be a privacy breach for retailer 2. And that's the reason why retailers wouldn't want to share data with each other, because there is an end user involved in here. And there's a lot of very sensitive stuff that has been going on in the last few years. Things like GDPR is enforcing a lot of retailers to be very careful about how they deal with end users' data. So we still like to share information kind of across retailers to kind of help with our models, but we don't want to breach anyone's privacy. So let's see. Yeah, so retailers not directly comfortable sharing data. So we can't actually use the previous method to directly aggregate data. And in this scenario, we have to preserve the privacy of the end user. And so the solution that we come up with is, how about let's try to aggregate at the model level. All right, so pretend that we have this magical way of training private models. And the idea of a private model is that once the model is trained, pretty much all the information that you would want from the data set is captured inside the model. But it is impossible, or statistically very unlikely, to reverse engineer the model to find out the specific details of any row of data that it was trained from. So in other words, we're protecting the privacy of end users, each individual user, through this private model, but we're still kind of opening up the actual predictive capabilities that we would have gotten from using this data set. after we train these private models, and I'll kind of talk about how we train these private models in a bit, but if we were able to train these private models, the next step in order to kind of share information across multiple customers is we train a boosting model on all these smaller private models. So the idea here is that for example, if we're training a model for retailer 1, we would take the data from retailer 1, the features, we feed it to all the private models, and we feed the output of the private models into a boosting model, such as XGBoost. And we train this on the labels from the original data. So effectively, we're training an ensemble on all of the private models. And that's it. And that's really how you can share information across multiple customers without actually sharing the data itself. Now, there's one question left. How do we train this private model? This is the crux of this method. And to understand that, how do we train these private models, we kind of have to step back a little bit and think about what does it mean to preserve privacy. And in order to answer that question, we have to go back a couple of decades because people have been thinking about how to preserve privacy in the statistical literature for a very long time. So let's look at what they came up with. So first of all, we have to put a definition on privacy. So maybe a first stab at putting a definition on privacy is maybe any statistical query should not be able to reveal anything new about any individual. But this is not necessarily the most useful definition because what this actually means is that, for example, if we query what is the average salary of a data scientist in North America, we will get some kind of answer, and then because my answer would be close, would be somewhere around that number, we can say that we have learned something new about Eddie, which means that it has breached my privacy. So that's not really useful because any kind of population statistic that we learn is defined as a privacy breach. So we can't use this definition because if we do, then we will have no utility out of any statistical analysis. So this is not good. So perhaps a better definition is this, is that if we have learned anything new about an individual, we would have learned the same thing if the individual was replaced by another random member from the population. So what does this actually mean in practice? It implies that we can learn about the population, but we don't learn anything about any one individual. And this is the key to the differential privacy work that I'm going to talk about later. But notice how this is just a definition. This is how we chose to define privacy, and this is how most people agree that privacy should be defined. All right. So how do we actually implement something like that in practice? So here's the first attempt at preserving privacy. So in the 2000s, a lot of companies really embraced the idea of anonymization or de-identification. And a lot of people believe that this is the right way to preserve people's privacy. And the way you do it is that if we're about to release a data set with compensation data, we find what are the most sensitive information. And in this case, it would be information that could identify an individual. In this case, it would be the names of the individuals. And so we can say, well, let's replace those names with random characters. And now, if we were to do any kind of query on this database, we wouldn't be able to know from whom the data actually came from. Unfortunately, this doesn't always work. And it breaks down when we have third-party information. So if for some reason, if somehow we got third-party information that Alice is the only woman who worked at this company, we can simply ask the database, what is the average compensation of women in this company? And the database would naively tell us $80,000. And now we would have known that Alice made $80,000. And that is a privacy breach, so we cannot do that. So how do we actually deal with this when So how do we actually preserve privacy in the face of potentially unlimited amount of third-party information as we have here in the real world? Well, the best way to explain this, I think, is through an example. All right, I can barely see everyone because of the bright lights, but let's give this a try. Raise your hand if you have ever cheated on an exam before. All right, we got a few very brave souls. Thank you for being very honest. Let me try to ask this question a little differently. I want you to pick a random number in your head, from 1 to 10. Now, hold in your head. All right, you got it? If your number is odd, I want you to answer truthfully. And if your number is even, I want you to pick another random number from, let's say, 11 to 20. And if your second random number is odd, I want you to always answer yes. And if your second random number is even, I want you to always answer no. All right, everyone got this? All right. So raise your hand if your answer is yes. Great. I'm seeing maybe 40% of people has raised their hand. OK, awesome. So what just happened? So first of all, wow, I shouldn't have put all those three up at the same time. So first of all, a lot more people participated. Because now everyone has plausible deniability in whether they cheated on a test or not. And second thing is that we can actually back compute the actual number for the actual probability that someone has cheated as a population. But we can't actually point to any one individual and say that you've cheated on an exam. And exactly how much that is, we can kind of work backwards, 0.4 minus 0.25, which is 0.15 times 2, so that's 0.3. So it turns out that in this crowd, 30% of people have cheated on an exam before as a population. So fun statistic, a study has shown that 60% of the people has ever cheated on an exam. So I think we have a really good crowd here. We effectively achieved this plausible deniability and allowed kind of more people to join this, this very sensitive query by injecting noise. Right? We injected random noise into our queries. Sorry, into our answers. And that is kind of the key of differential privacy, is injecting noise. OK, so can we take this idea of injecting noise to also kind of address the previous problem that we came up with the compensation data? OK, so now we have a third-party information that Alice is the only woman in the company. And our query is, what is the average compensation of women in the company? Well, our answer can be $80,000, and then plus minus some random amount. In this case, I chose to return $80,000 plus minus negative $80,000 plus or positive $80,000. And so every time you query the database with this question, you'll get back a different answer. You'll get back maybe 10,000 or 120,000 or 60,000, so on and so forth. OK, so now an adversary has very low chance of actually finding out the true salary of Alice. But unfortunately, if I were not an adversary and I'm trying to query this data to do something good, I'm not able to get any useful results. Now, by injecting too much noise, we can actually make our mechanism useless. So we've effectively lost all utility. So intuitively, there's this trade-off between utility and privacy. So if we inject more noise, we can preserve more privacy. If we inject less noise, we can have more utility at the risk of privacy. So then the natural question to ask is, how much noise should we actually inject? So to answer this question in a quantifiable way, we need a way to quantify privacy. And that's when we came up with, well, that's when the statistical literature came up with differential privacy. And this is a definition coined by Cynthia Dwork back in 2006. So this might seem like a daunting equation, but I find the easiest way to explain it is if we move that probability on the right to the left. So we just switch it from the right to the left, like that. What you'll notice here is that these two probabilities look effectively the same. The only difference, actually, let me explain something about this first. So the A here is a random algorithm. So that is, for example, the salary of Alice plus minus a random number. So every time you sample from A, you get a different number back. So we call this a random algorithm. And really the big difference between these two probabilities is this D and D prime. We define D and D prime to be neighboring data sets in the sense that D and D prime differ by at most one row of data. So what does this actually mean on an intuitive level? Well, if D and D prime differ by at most one row of data, then this ratio is kind of saying what is kind of the maximum effect that one row of data can have on the distribution of the output of our random algorithm. And we can see that this ratio is bounded by e to the power of epsilon. Now, we usually set epsilon to a very small number. And when e to the power of epsilon, and when epsilon is a small number, e to the power of epsilon is approximately 1 plus e. So, again, 1 plus e is still very close to 1. And so when epsilon is small, we're effectively saying that any small perturbations that you make to the data, if you kind of add one row, remove one row, or swap out one row, the distribution of your output from where the chance of any event occurring is effectively the same from your random algorithm. OK, so hopefully that gives you an intuitive understanding of what this equation actually means. So harking back to a few slides ago when we kind of talked about what we would like the definition of privacy to be, it said if we learn anything new about an individual, we would have learned the same thing if that individual was replaced by another random member from the population. And here, that concept is captured by this D and D prime. So we can actually swap out any member of the data set with another member from the population, and our random algorithm will still effectively produce the same result. Right. So what does this mean in terms of machine learning? So before we were talking about these random algorithms as like statistical queries, like taking the average or taking the quantile and so on and so forth. Well, in terms of machine learning, this random algorithm is a model training process. And our D and D prime are our data sets that we usually use. And this effectively is saying that the probability of learning any set of parameters for your machine learning model is roughly the same whether a row of data was removed, added, or exchanged. All right. So we have this epsilon parameter that we introduce, and we have this random algorithm. Kind of how do these two things play together in practice? So the first thing you do in practice when you're using differential privacy is that you have to choose an epsilon value based on your data and based on your business requirements. So usually you want to set this as low as you can. And then you have to choose a differentially private algorithm to actually use. And we have a lot of differentially private algorithms, and they have different upper bounds on how much noise that you need to inject. So the idea is that depending on your application, you want to select the algorithm that injects the least amount of noise. And remember, injecting least amount of noise means that we can achieve more utility. So choose some DP algorithm, inject some amount of noise. And then in the last step, we have to check that our final algorithm has enough utility. Right? Have we injected too much noise? And if we have, maybe the final differentially private algorithm is not useful at all. The differentially private model is not useful at all. Okay, recall the solution that we proposed for Bluecore. We were training differentially private models at the first step, and then we were doing this model aggregation later. Okay, let's walk through how we actually chose the differentially private models for Bluecore in this case. So I should mention that the task here is a logistic regression problem. So the private models we're training is that we want to train differentially private logistic regression models. Okay, so the first thing is that we choose some value of epsilon. So in practice, we just chose various values of epsilon because we wanted to first search what is the value of epsilon that that can actually give us a good amount of utility. And I'll show you that kind of trade-off later on. So Bluecore uses logistic regression for this problem. So we chose a specific method in differential privacy called the boson method by Xi and al. From 2016. So this specific method requires less noise than a lot of the other alternatives, but it requires the loss function to be strongly convex. And it turns out that logistic regression with an L2 regularization is strongly convex. So luckily, we were able to use this method. And let me just illustrate it here. This is the boson method. And after we do this, we want to check if the resulting model has enough utility. So, and here's the experiment that we ran. So on the x-axis, we see various values of epsilon. And for every value of epsilon, we would train maybe like 100 different models, and we would kind of measure the AUC for the end task. And as you can see, for very small values of epsilon, we had almost no utility. It's effectively doing random predictions. The AUC is hovering around 0.5. And if we add no noise, we achieve the result on the far right. And somewhere around kind of 0.01, 0.02, we achieve pretty good results, even using differential privacy to train our models. And so we will at this point kind of go back to the business unit and say, does 0.01 as an epsilon value make sense? Is this enough to protect the privacy of our customers? And I think our experiments later on are using epsilon values of 0.01. We ran this across 30 retailers from Bluecore system. And we saw a pretty significant lift in the predictive accuracy of this model. So we got something like a 30% average lift for new customers. So these are cold start customers without a lot of data. It would make sense that it helps them the most. And we saw about a 10% lift for all customers overall. So here, the orange bars are kind of before we use differential privacy model aggregation, and blue is afterwards. I should mention for this technique and the previous technique, we do have papers for them. So the link is in the slides that you can find after the talk. All right. So we use this very specific method to train differentially private models. But you can actually use this today. So there's a very popular framework, you might have heard of it, TensorFlow. And TensorFlow has a module within it called TensorFlow Privacy. And TensorFlow Privacy has implemented a couple of really popular differentially private models, differentially private algorithms. One's DPSGD, differentially private stochastic gradient descent, and the other one is Pate. And both of these are very general methods, and they work quite well for a wide variety of models. We are currently in the process of merging our implementation of boson into TensorFlow Privacy. And again, boson is a very specific method. You need to have convex loss functions, and it works for logistic regression and SVMs, as far as I know. And expect to see this work done approximately sometime in the summer of this year. All right, so I'll give you a summary. What do we do here? So we trained differentially private models for each customer, and then we ensembled the private models. And that really is everything you have to do to make this work. And you can train the differentially private models in any way you want, right? You can use any differentially private algorithm to train it. Kind of giving you more and more intuition about differential privacy, differential privacy, the reason why it works is that it relies on injecting noise. And it can inject noise at different levels. We can inject noise at the data level. We can inject noise at the kind of the gradient level. We can inject noise at the final output. All of these things work. But the main idea is that the reason why differentially privacy works and how it kind of guards against all these external third-party data is that it relies on injecting noise. And the rough intuition you should have is that the more noise that you add, the higher the privacy guarantees, but the lower the utility. And there's this fundamental trade-off there. So it's not perfect. In practice, some of these differentially private algorithms rely on very strict assumptions. And when they have strict assumptions, we're able to mathematically derive tighter bounds on the noise that we need to inject. And this, in turn, allows you to train privacy-preserving models with more utility. And finally, as a practitioner, you should consider using libraries such as TensorFlow Privacy instead of rolling your own implementation. So we took a very long time to figure out how do we implement bolt-on, and now we've done it, and we're about to merge it in. You should just use it. Really, there's no reason to roll your own. All right. So as I said at the beginning, there are 3 key takeaways from this talk. And I just want to reiterate them to drive it home. The first one is why simple aggregation of data doesn't work and how we can do better. All right, let me go back to this point. So just to recap, simple model aggregation doesn't work because there could be potentially negative transfer. And the way that you can avoid this problem is by doing domain adaptation. And in our case, we use a very simple domain adaptation method by weighting each data point. And that seemed to work pretty well for us. The second takeaway is that I wanted to give you this intuitive understanding of differential privacy, the trade-off between the noise that we inject and the utility that we can derive, and how you actually use differential privacy in practice. And finally, I wanted to just highlight this, if anything that you should take away from this talk, it should be this high-level understanding of these methods and decide if they can actually be applied to your organization. So the first point is aggregating cross-customer data will probably always give you better model performance. So if you can figure out a way to do it, that would be great. The second point is that if you have the data rights, you can simply use something like the instance-based transfer learning method to aggregate data together. And lastly, if you would like to preserve end-user privacy, consider using the model ensemble transfer learning method with differential privacy. And that's all. I wanted to give a big thank you to all the companies that we've worked with, and here are all the people we collaborated with from these companies to make this work come true. And there's our Twitter, so follow us on Twitter. And I think we have a couple of minutes left. And if you have any questions, please, I think there's a mic over there if you want to go ask any questions. Yep. Yeah, please go to the mic so I think they can hear you too.
I have 2 questions. One is, when you say the target and source data, can you clarify how you differentiate between the target and source data? That's the first question. The second question that when you say that you put in the weights, are you saying that you put in the weights on the cost function, or how you specify the weights?
Right. So go back here. So in general, we are trying to do quote-unquote transfer learning on the data level. So when I say target and source, the target domain is a data set that you're trying to make a prediction, you're trying to make a predictive model on. And the source domain is kind of the data that you're trying to use to help you with your prediction task. So the idea is that your source domain might be something very close to your target domain, but not exactly the same. And you want to try to adapt the source domain to kind of, in this case, just pick out the data points that are most relevant to your target and use those to help you with your classification task. Does that make sense?
So you're saying that you use the source domain to train the model and try to use that to apply your target domain?
Sorry, no, we're trying to aggregate the data from the source and target together and using the entire aggregated data set to train a model.
And then to apply to target?
Yes.
Okay,
so sorry, we're trying to train it on the target task, but say if the source domain has positive and negative examples, and we're going to use the positive data points from the source domain as well, if they have, but the source domain, every data point has a weight on it. So you can have positive example from the source domain, and if it has a lot of weight, we'll probably use it. If it doesn't have a lot of weight, it won't have a lot of effect in the final model.
Yeah, I have difficulty understanding the use case. Why don't you just put them together and then train it?
So if you simply put them all together and train it, we can potentially have this problem here. So we have our target, which are the squares, and we have the source, which are these stars. And if you simply put them together, because the distributions of these two data sets are different, the source domain might actually overwhelm the target domain. And you would probably come up with an incorrect classifier, or a classifier that would do worse on your final task.
Okay, so when you say that putting the weights, are you putting the weights on the cost function?
Maybe the math here will make more sense. So we're putting the weights here exactly on the green area. You can see that. So yes, so we're putting the weights as we're training it. The weights is part of the cost function itself.
Okay.
Yeah.
Cost function.
Yeah.
Okay, thanks.
You're welcome.
Hi. Thank you very much for the talk. It's very interesting and informative. I've got a really naive question. Like the example you gave, like the Alice, if you know that's the only woman in a company, right? By ingesting some noise in the data, you will protect the privacy a little bit better, right? So, but if you know that, if you know the information, wouldn't times, and if you follow a distribution, will still get you like the information you need.
Yes, you're absolutely right. So that is definitely a problem with some implementations of differential privacy. If you keep querying the data set over and over, and you look at the expected value, you will eventually breach privacy. So there's something called a privacy budget. So every time you are querying, you're kind of adding on to this privacy budget. This is something that it's maybe a little bit more detailed than I would like to get into, but eventually you will kind of go over this privacy budget, and then you would have breached privacy. So yes, you're right. Eventually, if you query this over and over, you will breach privacy.
Okay.
Yeah.
Gotcha. Thank you.
Yep.
Thanks very much. Really interesting stuff. The first scenario where you describe different distributions in the target versus the source data set sounds very similar to me to kind of a classic statistical problem in adjusting for selection bias in quasi-experimental design. Propensity score analysis, have you ever kind of looked at parallels with that field? I think what you're doing is taking it a little bit further, but you're essentially, with propensity score matching, you're predicting membership in one category or the other based on characteristics of the cases, and then using that prediction from a logistic regression to match your source and target data. Am I off the mark here, or does that sound like it's a similar
That sounds really similar, but I haven't heard of the method you mentioned before. I'm definitely interested to look at it afterwards.
You might take a look just to kind of align your method with the literature. I think you're adding something interesting to the approach. I think it's a Don Rubin method. It goes back a little ways, but it's been well studied.
Okay, thank you so much. All right, thank you, everyone.